Right, this one. Okay. So this was the question. Right. So there are this is a inclined plane or a plank on the inclined plane. You can consider the entire inclined plane is moving up and down like this, back and forth like this, but it's at a high frequency, right? So very low time period. The time period of motion is so low that over a period of time, this particular block, as it moves down, acquires a steady motion. So it will keep moving with a steady velocity. Okay, right. So what is the value of that average velocity is asking. Okay, so the average velocity of that particular block over a long period of time, right? Assume this inclined plane is long enough for this to acquire that steady motion. Okay, so in this question, what I will try to do is I will assume certain axis. Okay, right? So the block is going to move down, right? So I'll take this downward direction as the positive x-axis. Positive x-axis. Okay, right. I'll draw the diagram again, turning it into the almost horizontal plane, right? So I'll assume I'm drawing a diagram in the x-axis direction. Okay, so let me move. Okay, it's the block is moving. So in this new diagram, this is my positive x direction. Okay, right. So on the block, the forces that would be acting in the positive x direction towards your left, and there is a plank underneath, right? Let me draw the plank in a different color now. So this is the plank. Okay, so a constant force that would be acting on the thing would be mg sine alpha. Mg sine alpha is actually down the incline. I'm drawing this entire thing by rotating so that I can easily visualize the x-axis. Okay, I don't want it to be in the downward direction. You could have done it downward, but this is how I'm using it. And the plank will be moving back and forth. There will be two motions that would the plank have, right? So without loss of generality, I will take t is equal to 0 is the instant when plank is at rest. Okay, right? So at t is equal to 0, assume velocity of the plank vp is equal to 0. And also I'll assume vp is given by a sinusoidal motion of v naught sine omega t. Not only that, in steady state, I'm assuming that block is moving towards leftward direction. Leftward is the down the incline direction with a v steady velocity. Okay, so this is how I'm assuming this particular motion. Now, which means if I draw the graph of Vp versus time, velocity of Planck versus time, it will look like this. Okay, right. So graph the sine function, right? So something like this, where capital T is the time period of the oscillations of the Planck. So I'm assuming velocity of Planck moves from 0 to a peak value of V naught. Now, between this 0 to V naught, I'll end up having, let's say, a V steady also. This V steady is the velocity of the block. Okay, so let's try to analyze how the motion of the block will be during this steady motion. So I'll mark a point here on the graph, here, okay, on the graph, this part. So that is, let's say I mark it as some small t naught. Okay, right. So what does t naught mean? T naught is time taken for velocity of Planck to change from 0 to Vs. So 0 to Vs is the time taken, right? And if you extend this variation onto this side of the graph, somewhere here, right? From Vs again to 0, this would be also T naught. Okay, so whatever time the Planck takes to rise from velocity of 0 to V naught is the same time it takes from going from that Vs to 0. Okay, so I can finish this statement by saying T naught is time taken. T naught is time taken for the velocity of Planck to change from not just 0 to Vs, but also vice versa. Okay. Why this T naught is important? Let me talk about that. Now, the Planck is, let's say, at t is equal to 0, this was the instant, right? So from 0 to T naught, from 0 to T naught, what does the Planck do? Planck will start increasing its velocity, right, from 0 to Vs. During that period, in which direction will the friction act on this block? When the Planck is slow, the block will have a friction acting in the backward direction, right? Because on the Planck it will be acting in the forward direction, right? So that is from 0 to T naught, this period. So maybe I'll just shade that diagram, okay, right, for you. So during this period, this shaded region, that is the period when the friction acts on the block in the backward direction. Okay, right. Can you tell me in the other shaded region of T naught again, in which direction will the Planck block have the friction? I think it is the same, right? Because as long as the Planck is slower than the block, as long as the Planck is slower than the block, I think you'll end up having friction acting in the backward direction on the block, right? So what is that period in one oscillation, right? So I'll just write in one oscillation period or one capital T period, T by 2, which is this half period, this is T by 2, minus 2 T naught period is the period when mu mg cos alpha acts on the block in forward direction. Okay, right? Whereas the rest of the period, which is T by 2 plus 2 T naught, that is the rest of the period. Total time is T naught, T, and T by 2 plus 2 T naught is the period when mu mg cos alpha acts on the block in backward direction. Okay, so let's try to now see what are the forces that are acting during the entire period. Mg sin alpha acts in the forward direction. Okay, so for mg sin alpha it is capital T, right? And mu mg cos alpha will have backward and forward actions in two separate halves. So for steady motion, on an average, net impulse in 1t should be equal to 0. Net impulse acting on the block in one time period should be equal to 0. That's the idea. So if I go to the next page, so how do you write the net impulse? Net impulse in the downward direction should be equal to net impulse in the upward direction. So let me say total impulse in the downward direction should be equal to the total impulse in the upward direction, blue color. So the red part, in the downward direction, the impulse is due to mg sin alpha, okay, multiplied by capital T, because that's a constant value. Whereas for mu mg cos alpha, that is the friction value, that would be acting only for T by 2 minus 2 T naught, right? Whereas this should be equal to the blue part, which is this part, right? Mu mg cos alpha in that direction would be acting for the rest of the period, right? So this would be t by 2 plus 2t naught, right? So when you rearrange this, you'll end up having value of t naught is equal to, I just made the calculation here. This would be capital T into sine alpha divided by 4 mu. I took cos alpha is approximately equal to 1. I'll even make sine alpha as alpha at the end. Okay, I just wrote it as sine alpha. So you could have just written this part, right, as tan alpha also if you want to. Right. So this is the value of T naught. And at the same time, how do you get the value of T naught? V Planck is equal to, we already know V naught sine of omega, let's say T. And when V Planck, we said, is equal to value of V study, the value of T was supposedly T naught. Okay, so I'll substitute the value of T naught that I got from this equation, this blue colored one, into this one. Okay, so which means I end up having Vs is equal to V study is equal to V naught sine of omega is 2 pi by T and T naught is T sine alpha divided by 4 mu. So T gets cancelled and you'd get V study is equal to V naught sine of pi sine alpha divided by 2 mu. Okay, and if you're not getting these in the options, that is, you can further take. He said mu is very large, right? Value of mu is very large. You could say tan alpha is in comparison to mu very small. So you can make further approximations. This entire thing in two forms. Okay, so you can make this sign go away and sine theta is theta, and then you can search for this option in the options. If this is also not existing, you can also write this as sine alpha as alpha. This would be the another approximation. So depending on which of these three are in the options, I think even tan alpha is fine, because sine alpha, tan alpha for a very small alpha would be the same. So, but yeah, this is how we go about the business. Okay, right.